One of the biggest advantages of the IROA methodologies is the accurate identification and quantitation of metabolites. This presentation shows how accurate compound identification is achieved using the IROA ClusterFinder software. The labeling procedure is discussed in the section How IROA Works. Once labeled with the 95% C13 and 5% C13 media, all of the biological components in the control and experimental sample will carry unique signatures, and this means that the control sample can be directly embedded into and prepared simultaneously with an experimental sample and analyzed as a composite. This reduces the number of samples to be analyzed in half and also removes sample-to-sample variance. This slide shows the anatomy of a 5-carbon molecule following IROA labeling. Each of the 5 carbons has a probability of 98.8% that it is a C12 and a 1.1 probability that it is a C13. The pattern of peaks is calculable and therefore may be used to determine the number of carbons in the monoisotopic peak. The C12 M+ peak, located at 162.0755, and the C13 M- peak, located at 167.0921, clearly indicate that this is a 5-carbon molecule. The corresponding M+1 and M-1 peaks are a mass difference of 1.00335, the mass difference between a C13 and a C12 isotope. Once an IROA peak is identified, it can be matched to the correct shape, which is confirmed by the other half of the pair. Note the carbon envelope shape of the molecule. For a more thorough discussion, please refer to the section on carbon envelopes. Another way to calculate the number of carbons in a molecule is by measuring the M+1 and M-1 peak heights relative to their monoisomeric peaks by the binomial expression shown here. This is not sufficiently accurate when all atoms are present at their natural abundance, but at 5% C13, the dominance of the carbon makes the other atoms less significant. Therefore, the M+1 will be approximately 26% the height of the monoisotopic peak in a 5-carbon molecule. The IROA ClusterFinder software finds IROA peaks based on the fact that all IROA peaks are mathematically calculable. When both C12 and C13 IROA peaks are present, each set of carbon isotopomers, C13 and C12, reliably and accurately counts for the other set, providing a redundant quality control check. A short, less than 15-minute mass spectral data set will contain in excess of 800 million peaks, yet using the guidance of IROA peaks, the ClusterFinder software will extract only those peaks of biological origin. This results in a dramatic reduction of data. By using the information content inherent in the extended isotopic envelopes using the IROA peaks as guideposts, the ClusterFinder software pairs all remaining peaks and identifies all pairs. Depending upon the sample attributes, the IROA extracted dataset will list between several hundred and a few thousand IROA peak pairs. When a reasonable mass spec resolution is employed during analysis, the mass and the number of carbons is used to unambiguously assign a molecular formula for the monoisotopic peak. Because the isotopic dilution distributes molecules over a number of masses, the sum of the base peaks and their associated isotopic peaks are used to calculate their respective areas accurately. ClusterFinder uses the summed areas to easily calculate their ratio. Datasets are normalized by using an IROA normalization ratio, which is taken as the ratio of the total ion count for all the C12 and C13 clusters respectively, which represents the relative size of the two original control and experimental populations. The use of the IROA carbon envelope ensures that artifact-based errors are avoided, and compounds are correctly identified using accurate mass and the number of carbons. In summary, the IROA ClusterFinder software automatically removes all artifacts and accurately identifies and quantitates all biological extracted compounds to report differences between control and experimental samples, which can then be used as potential biomarkers.